Alrighty, let's get after it. We're going to talk more about volumes today, but we're going to produce these solids in a little bit different manner than what we did the last couple of days. So now what we're going to do is we're going to look at a region, right? Some area. So for example, the one I have here, the shaded region R, it's bounded above by some curve to the left and right by x equals a and x equals b and the x-axis. Well, what I want to do now is I want to take that region of area and revolve it around the x-axis. And when I take that region and I revolve it around the x-axis, I'm going to get a three-dimensional shape, right? It's kind of difficult to draw, but this is pretty decent drawing of what I got here. It almost looks like a vase that is sideways. Now, sometimes that's kind of hard for us to see in the beginning. So let's go ahead and pull up Geogebra real quick. I have a very similar type deal where this is the shaded region. It's under this curve, which is a little bit different than the curve I just showed you in the notes. And it's bounded to the left and to the right by certain x values. We'll call them A and B and the x-axis. So now if I take this region and I revolve it around the x-axis, take a look over here. I can kind of somewhat do this simulated. Hopefully it looks smooth. You're going to get a solid, right? And so there it is. And so I can mess with the perspective. All right, and you can kind of see the shape of this solid here. All right, not 100% sure what that thing would be. Some sort of funky hat, maybe. I don't really know. But nonetheless, that's the solid you get. Now, what we're going to want to do every time we do these volumes of solids that are created by revolution is we're going to want to look at cross sections. And we always want to look at cross sections perpendicular to the axis that you're revolving around. All right, so I revolved around the x-axis. So what would my cross sections be? And here I'm drawing a whole bunch in for you, right? I'm kind of slotting it. Maybe I draw a cross section to the very right. Maybe I draw a cross section in the middle. When I say draw, I mean you're kind of slicing this figure. Now, no matter where I slice this figure, right, you can kind of see it here, right? That black thing, that's the cross section. I slide it back and forth. No matter where I draw in this figure, your cross section is going to be a what? Right? And I'll kind of give you this look right here. And hopefully you're saying it's going to be a circle. And that kind of makes sense because the way this thing was created, it was revolved around the x-axis. All right. So let's go to our notes here, and where it says every cross section sliced perpendicular to the x-axis, right? And more importantly, the axis of revolution, that's going to be a circle. Now, and I'm talking about, I kind of drew in a three-dimensional disc here, right? We're just talking about the circle right now, right? So just the face of this. So what would the area of the face of that be? Well, if it's a circle, then it's just going to be pi radius squared. But maybe we can do better than that, right? So what's the radius? Well, the radius is going to go from the axis you're revolving around, right, to the outer edge, to the curve. It's going to actually touch the curve. So now, depending on where I drew in this disk, that's going to kind of depend on what the radius is. And so the radius is dependent on the x. In fact, this distance is the functional distance between the x-axis and the curve, right? And that curve is y equals f of x. So hopefully you're saying, oh, the radius is just the curve. It's the top curve. It's f of x. Depending on what x is will depend on what my radius is, right? If I drew in a circular cross section here, that's going to have a different radius than if I drew a circular cross section there, and so on and so forth. So it's dependent on x. Great. So now I'm not really interested in the area of the cross section. I want to make a three-dimensional shape. So what I'm going to do is I'm going to make a disk. And so in order to do that, it's kind of already done for you here, but you basically just kind of give this thing a thickness, right? And so now this shape here, now that it's three-dimensional, all right, is going to be our disk. And if I drew it lying flat, it looks something like that. It's basically a cylinder, right? So what's the thickness that you're giving it? Well, that's a change in x, right? So it's going to be delta x, right? We can call the thickness delta x. So then the volume of one representative disk, the one I drew here, say, it's just going to be the area of the cross section, right? Which would be that times the thickness. And this should start to seem a lot like what we've been doing recently, right? You got an area of a cross section times the thickness. That gives you the volume of a particular cross section. These cross sections happen to be disks. Couple of things. Guess what? You revolve around the x-axis. Your cross sections are perpendicular to the x-axis. That means everything's in terms of x. So we're going to have a delta x. Take a wild guess what it would be if you were perpendicular to the y-axis. In other words, you revolved around the y-axis. Hopefully you would say you'd have a delta y for the thickness, all right? So now it says, let's add up the disks to get an approximation of the volume. Can we do better? So this is kind of like, all right, so how would I do this, right? So I can basically say, all right, so I have one representative disk would look something like this, and I can put like a super or subscript on this, right? And call this delta x, and I could do delta xk, but I can make them uniform. And I want to sum these up from the first disk to the nth, depending on how many I want to use. So now think about me drawing a whole bunch of consecutive disks here stacked up to build this shape. Now, they wouldn't look smooth because they had thicknesses, right? The larger the thickness, the less disks, the more rigid it looks. The smaller the thickness, the more disks, right? The smoother it looks. So this would be an approximation for the vine. But the question is, can we do better? Of course we can do better, right? So what we would want to do is we would want to add up all of the disks as the thicknesses went to 0, right? So that would be something like the limit of the sigma from the first one to the last one of this expression over here, right? And then I'll say as the maximum delta xk, or just as the delta x, since they're uniform here, goes to 0. Or maybe I say as n goes to infinity. What is that the definition of? That is the definition of the integral. So that is going to be equivalent to integrating from a to b of f of x squared dx, and then I have my pi, right? I can't forget about my pi. Okay, and that's it. And that's actually called the method of disks. Sometimes you'll see it in textbooks as the integral from a to b of pi big R squared dx. Sometimes you'll see it with the pi pulled out. All right, why big R? We'll take a wild guess what big R stands for. It stands for the radius, and it is implied that R is a function of x. So it probably would have been better to write big R of x squared, but sometimes you'll see textbooks do that. All right. We had a demonstration here on Wolfram. You can actually go to that website and just type in volumes using disks, and you get a couple of demos. I didn't really love them as much as I like the Geogebra one. All right, so let's just get after it. Let's do one. So it says find the volume of a solid obtained when the region under y equals radical x over 1/4 is revolved about the x-axis. So again, when we were doing those problems the other day, I always had you underline something, right? And that was, what are you perpendicular to? That's what you would underline. Well, now you underline, what are you revolving around? So if you're revolving around the x-axis, this is me drawing an arrow, not a G. If you're revolving around the x-axis, that means everything has got to be in terms of x. You're integrating with respect to x because your thicknesses of your cross sections, which happen to be perpendicular to that axis of revolution, all right, would be delta x's. So that's huge. So all right, so let's get going here. So let's draw a picture. So pictures on these sometimes are a little tricky, and they're not super important, but I do like doing them for no flow. All right, so we all know what y equals radical x looks like. That's nothing crazy. So just like that, that's going to be y equals radical x. And now I'm only looking at it from 1 to 4, right? So I'm looking at it from 1 to 4. And this right here is the region that I want to revolve around this x-axis, okay? All right, so normally I just draw one picture. I don't draw both, but I'm going to draw both here. So now I'm going to draw my best attempt at what this shape would look like. So these aren't too bad to do, although it's a little tricky with this little pen and tablet thing I got here. But basically you draw the curve, and then you mirror image that curve in whatever you're revolving around, which in this case is the x-axis. That won't always be the case. And now we're doing this from 1 to 4. So kind of what I do here is I go up here, and I do like a little archy thing. Okay, curve it, hit the x-axis, and then curve it back. All right, I'm going to do the same thing here. Curve it, and then curve it back. And then I'll curve this the opposite way. And the way I guess I have my perspective, then this would technically be like dotted. All right, so hopefully you're getting an idea that the shape here would be this thing. All right. What would this look like? Some people say it's a bowl, but remember, we want to think of these as solids. So it'd be like a solid bowl, which really isn't a very good bowl. I don't know if you put it sideways, it's like one of those things that elephants stand on at a circus. I'm not 100% sure, but this is the shape. So now the question you have to ask yourself when you do these solids by revolution is, all right, let me look at a cross section perpendicular to the x-axis. What is it? All right. And you're really going to only have two options in this class. One is a washer, which we haven't talked about yet, so it can't be that. And the other is a disc. And so it would be a disc. So if I kind of drew in a representative cross section right here, that's actually not that bad, guys. That's just one representative cross section. Let the whole world know, hey, that is a disc. Okay. Now, how would I know it would be a disc without having to draw this funky shape? Well, think about it. I'm revolving around the x-axis. If there is no space between the area that I'm revolving and the axis I'm revolving around, then I'm going to get a solid disc. And that's what I have here. So that would tell you method of discs. Now, what do I do? Well, I'm going to start off with the volume of a representative cross section, which I can call now representative disk. All right, notice this is exactly how we set up the other problems. So, all right, well, what is the volume of a representative disk? Well, it's the area of the cross section, so pi r squared, and then delta, whatever I'm perpendicular to, which in this case is the x-axis. So that's set up. So now what's the radius? Well, the radius is the functional distance from the x-axis to the curve. So that's just touching this curve. So my radius is just radical x. Now that would be the volume of just one disk. What do I want to do? I want to add them all up as the thicknesses go to 0. So I would say, okay, volume of the solid, I'll pull the pi out. Integral, I'm starting at 1, ending at 4. And then, oh, by the way, the square root of x squared, that's just going to be x. But maybe for no flow, I'll write this. Because a lot of times, this is what you'll start with. You won't show this ever. Notice I didn't write delta x here. It's dx because it's an integral. It's the thickness going to 0. I can rewrite this integral because clearly radical x squared is just going to be x. And now I can do this one by hand. All right, so if I integrate this, I'm going to get 1/2 x squared evaluated from 1 to 4. There's this pi out here. Okay, so I have the pi over 2 out here, fundamental theorem of calculus. First chuck in 4, right, minus, don't forget that 1/2 x squared. First chuck in 4 minus, then chuck in 1. All right, so you're going to get 16 minus 1, that's 15 times pi over 2. So you're going to get 15 pi over 2 cubic units, and that would represent the volume of this solid. All right, so very, very, very similar to what we've been doing, maybe a little bit neater, but it's still all about volume of a representative cross section. Okay. All right, so this is pretty neat. This is a little outside the box. It's derive. We just throw you to the wolves here. Derive the formula for the volume of a sphere with radius r. So, all right. So if you were to do this problem on your own, you'd have to be like, all right. So I probably have to set this up in a way where I got to think of this as an area that I'm revolving, maybe around the x-axis, to produce this sphere, right? So what shape could you revolve around the x-axis so that you would get a basketball, so that you get a sphere? And hopefully you're saying a semicircle, right? So if I go ahead here and let's go red, and I kind of drew just the upper portion of a semicircle, right, with a radius of r. I don't know what the radius is, so I'm going to call it r. So that would be like r, and that would be like negative r. So then what would the equation of this be? Well, back in the day when you did circles, it was like x squared plus y squared equals radius squared. And so if I solve this for y, I'm going to get r squared minus x squared, and then the square root of all that. That would be the upper branch. The negative square root would be the lower branch, but I don't care about that. Because if I take this region right here and I revolve that around the x-axis, I'm going to get a basketball. Okay, I'm going to do my best to draw this, but this one's definitely not going to look, I don't think at least, as good as that first one I drew, which I thought was pretty decent. All right. So how would you do it? So it looks something like this. It's a little bit more tricky. Mirror image it in the axis you're revolving around, and you're like, this looks like a circle, right? Kind of tough to draw this one. So what we can do is we can do like a little arky do there, right? A little arky do there. And, if I was good at shading, I would shade it so you can see the light, but I'm not going to do that. So that's what you'd get. So now, what do? You look at cross sections perpendicular to the axis you revolve around. Maybe I'm going to draw in this cross section right there. Okay. And you ask yourself, what is that? Is it a disc? Or is this thing that you haven't told us about yet a washer? Well, hopefully you're saying it's a disc. How do I know it's a disc? Well, because the region of area I'm revolving around and the axis I'm revolving around, I should say, there's no gap. It's flush. The area is completely flush to the axis I'm revolving around. So when that happens, I'm going to get this solid disc as a cross section. So you're like, okay, so method of disc. So how do you do it? Let's start with the volume of a representative disc. So volume of a representative disc. Well, it's the area of the cross section. So it's going to be the pi r squared and then times delta x. What's the radius? The radius is going to go from the x-axis to the curve. Well, that's this guy right here. That's radical r squared minus x squared. Okay, so that would be the volume of just one disk. So what do I want to do? I want to add them all up as the thicknesses go to 0. So volume equals, maybe I pull the pi out, integral. I want to start at negative r and I want to end at r. So negative r to r, right? If I square the radical, it's going away. So I'm just going to get right to it and write this. And then, of course, it's dx. Now, guess what? We can leverage some symmetry here, right? Because if this is truly the circle center at the origin, then this part of the shape, right? This part, I hope I don't mess this up, but this part of the basketball is exactly the same as the part to the left, right? So what can I do? I can then integrate from, and we've done this before, right? I can say, all right, volume equals pi, going to go to r squared minus x squared. All right, but now what I'm going to do is I'm going to go from 0 to r and then just double it up. All right, since I'm doing this by hand, that's not a bad move. All right, so now let's rock and roll. What do we got going on? Well, we got to keep going. So we got this 2 pi. Let's integrate. So now I'm going to integrate r squared, but it's with respect to x. So don't you dare say 1/3 r cubed, right? If r squared with respect to x, r is a radius. It's a number. It's basically a constant. So if I said, what's the integral of 5? You would tell me 5x. So if I say, what's the integral of r squared? You would say, oh, that's just r squared x, right? Because r squared is just a number. And now when I integrate x squared with respect to x, yes, that's 1/3 x cubed. And then all of this evaluated from 0 to r. So you're like, all right, this is looking pretty sweet. So you got volume equals 2 pi. And now let me chuck r in where I see an x. So r squared times r, that's r cubed minus 1/3 r cubed. Okay, that looks good. So now let me chuck in 0. Well, r squared times 0, that's 0. 1/3 0 squared, that's 0. So that's just going to be 0. So that part wipes out. And so what do I get here? Well, this is like 3/3 r cubed minus 1/3 r cubed. So last I checked, right, that would be 2/3 r cubed. And then you're like, okay, so then I multiply that, I'm going to get 4/3 pi r cubed. And hopefully there's some smiles on your face and like, oh my God, that's amazing, right? Because what is that? That's the volume formula for a sphere, and we just derived it using areas and calculus. That's bananas, okay? All right, let's rock and roll. Let's go to this next one. This is a calc question. I know that because it says calculated question in parentheses. All right, so if we were to do this, we'd want to put this in our calc and graph it, adjust our windows so that we're only looking at it from -2 to 2, and then it says revolved about the x-axis to generate a solid. So this right here, revolved about the x-axis, tells you that everything must be in terms of x. Find the volume of the solid. We're going to be able to do this in our calc. So, all right. if you go to your calculator, I already did it for us, right? I adjusted my y, so I got a little bit more curvy looking features here. And this is from -2 to 2, right? So this is the region and the x-axis, right, that I want to revolve. Um, okay, so that's what the shape looks like. All right, so let me just come back over here. And maybe I'm going to do one picture this time, just not to go crazy with the pictures. And this video is already way too long, right? So if we go ahead and we sketch this, all right, so this is my y-axis, this is my x, this is what I'm going to revolve around, and the shape looks something more or less like that. So now I have to kind of mirror image that here, and then I go to the end and I kind of arc, and then arc, and then I think the way I drew this would be dotted. That's the shape you get. Okay, so now what do I want to do? I want to draw a cross section perpendicular to the x-axis. I could draw it anywhere. Okay, I'm going to draw it right here. All right, so now what would it be? Would it be a disc or would it be a disc? It's a disc. All right. In fact, no matter where I draw this cross section, kind of like we did those retinal scans with the area problems, right? It would always be a disc. And in fact, even further, the radius of that disk is always going to be figured out the same way. It's the functional distance between the x-axis and this curve. So the radius is just whatever this f of x is. So if I start this problem off just like I started all the other problems off, volume of a representative cross section, which now I'm just writing as representative disk, it's going to be area of the cross section, so it's pi radius squared. That's pi f of x squared, right? And then times the thickness, which is delta x. Now, I don't want just one disk. What do I want to do? I want to add them all up as the thicknesses go to 0. So volume equals, pull the pi out, integral -2 to 2, and then I'll just write it in 2 plus x cosine x. That's my f of x. That's my radius squared dx. All right, since this is a calculated question, we do not try to be in hero and find the antiderivative. We just go straight to the calculator and we get our answer. All right, so let's see if I can do this here. So I already have this thing in y1, right? So I can quit out of this and I can go math 9, and I want to integrate from -2 to 2, and I have it in y1, so I'm going to do vars, y vars, function y1 with respect to x, and this is a common mistake here. Boom. Is that the answer? And hopefully you're saying no, because in y equals, you just have the function. You have 2 plus x cosine x, right? And that's not what I'm integrating, right? So what is it that I'm integrating? I'm actually integrating the function squared. So no big deal. You can go ahead here, do second enter, and then just come over here and blam. And is that going to be enough? Hopefully saying no, because what am I forgetting? Forgetting that pi. So I can hit enter now and then do the pi later. It doesn't matter, multiply by pi, or if I want to be fancy schmancy, I'll just go ahead and insert the pi right here, although that's not really being fancy schmancy. I don't know why I said that. And so, blam, there you go, 52.428. All right, so we're going to get 52.428 cubic units. And that's what the volume of the shape would be. Now, question to you is, could I have done what I did in the previous problem, which is say, hey, you know what, let me double it up and go from 0 to 2. All right, pause the video maybe and figure out what the answer to that is. And hopefully when you unpause it, you're going to say, no, you can't, because this function's not even. It's not symmetric to the y-axis. So it's not the same from -2 to 0 as it is from 0 to 2. So could not do that. If you wanted to do this one by hand, it would be a disaster. You'd have to multiply it out. And it looks like you probably would have to somehow, if you could, maybe use identities. But I think this one is not going to be fun. Okay. All right, so we got one more before the homework, so let's rock and roll. So it says, find the volume of the solid obtained when the region enclosed by y equals radical x, y equals 2, and the y-axis revolved around the y-axis. So very similar problem. So let's go ahead and do it. So let's sketch this. So there's my y-axis. Here's my x-axis. And now I got y equals radical x. So I know that looks something like that. And I got y equals 2, which that's just going to be a horizontal line, right? So that's going to look something like that. And then the y-axis, right? So this is the y-axis. So the region that we're thinking about or revolving is going to be this region here. So maybe I'll, since it's not that big, I'll just shade it in. So this is what we want to revolve. But now what's the deal? We're not revolving this around the x-axis. We're revolving this around the y-axis, which tells you everything's going to be in terms of y. Now, why is that? Well, let's draw the shape, right? So now I have to mirror image everything in a y, and it's, well, actually, that wasn't too bad. I'm going to get that, and then I'm going to kind of like archy do here, and I don't really know what the word archy do is, but I kind of do like a little arc. I stop, and then I come back in the other direction. All right, and I don't know what this would be. A solid tornado? Is that even a thing? Some sort of snow coney thing, like a weird looking Hershey Kiss balancing. I have no dreidel. I mean, I don't know, right? But this is the shape that you get. So now what do you want to do? You want to draw in a cross section perpendicular to what you're revolving around, perpendicular to the axis of revolution. So if I was to do that, right, I'm going to do it right here. What would it be? Well, it seems like it's always the same answer, right? It's going to be a disk. But notice how the disks are now. It's perpendicular to the axis of revolution. So yes, this is my disk, but now this disk has a thickness that is a delta y, and you can see it clear as day right there. And that means everything has to be in terms of y now. So this is real easy to get in terms of y. I can basically just square both sides, and now I have this curve in terms of y. So just like the other problems, start with volume of a representative disk. Well, it's going to be pi radius squared, but now it's delta y, right? So what's the radius? Well, the radius is the functional distance that goes from the y-axis to this curve. So it's touching this curve, but it's not radical x, right? Radical x would be that distance there, and that's not the radius. It's this horizontal distance, and that would be y squared, okay? It's the x equals on this curve. So your radius is going to be y squared. And so now to do this problem, I'm not interested in just this one disk, right? I want to add them all up from the bottom one here all the way up to the top one. So that is the process of integration. So I'm going to do volume equals. I can pull the pi out. Integral from where to where? Well, I'm starting these at y equals 0, and I'm ending them here, which is y equals 2. Okay? And then it's going to be y squared, that's radius, squared, and then dy. And now obviously I can spruce this before I attempt to integrate it. It's going to be y to the fourth dy. Now I integrate it. 1/5 y to the fifth from 0 to 2. Don't forget my pi, right? So that's going to be pi over 5. Pull that out. Let's go 2 to the fifth minus 0 to the fifth. 2 to the fifth is 32. So I'm going to get 32 pi over 5 cubic units. Again, I'm kind of glancing over the fact that why is it a disk again? Well, because look at the region that I'm revolving here, the solid region, it's light blue region, right? It's completely flush to the y-axis. There's no space between the area that we're revolving and the axis that we're revolving around. That's a big deal. That's why it's going to be a solid disk. That would not be the case if I tried to revolve this around the x-axis, right? That would maybe blow your mind a little bit. All right, but that's it. All right, so that is using disks, method of disks, to get volumes created by revolution. Today we only revolved around the x-axis and the y-axis. Tomorrow maybe we revolve around random lines. Okay, that was a really long video. I hope you watch it all. And this is a really nice picture. See ya.